Welcome back. This is Physics 104A, the Chapter 6 homework. Starting with problem number 12, the coefficient of kinetic friction is 0.21. How much work do you do when you slide a 50-kilogram box at constant speed across a 4.8 meter wide room? So the question is asking, how much work do you do? Let's list out the given information. Mu sub k, the mass of the box, the displacement, constant speed, which means that acceleration is equals 0. Let's draw a force diagram. Normal force up, weight down. We have the force of our push to the right and friction force to the left. Now let's do F equals ma. In the y direction, we have normal force up minus weight down equals 0. And that tells us that normal force is equal to mg. Now in the x direction, the sum of the forces equals mass times acceleration in the x direction. The push is to the right minus friction to the left equals, since it's a constant speed, 0 acceleration. From that, we can get the push equals the friction force, and we'll replace friction force with mu sub k n, and we'll replace n with mu sub k mg. Now, the reason we want to do that is because the question is asking for what is the work. Well, work is related to the force that we push with. So here we have work is the push force times displacement times the cosine of the angle between the push and displacement. Now, they're both going to the right, and so that's a 0-degree angle. So times the cosine of 0 degrees, which is 1. And now when we make substitutions, the push is mu sub k mg times displacement. And then we can just substitute in all the values. And we get 490 joules. Number 13, a crane lifts a 650-kilogram beam vertically upward 23 meters and then swings it eastward 18 meters. How much work does the crane do? All right, so here we have the force diagram. The crane is lifting upward. It's supporting the weight. Notice there is no horizontal force. Even when it's swinging to the right, the force that it's applying on the beam is still vertical. It's just holding it up. And so the crane force is up, the weight is down. Now when it's lifting, its displacement is straight up vertically. When it's swinging to the right, the displacement is straight to the right. So we have the sum of the forces equals mass times acceleration. And it doesn't say anything about there being an acceleration until you get to the last sentence. It says neglect friction and assume the beam moves with constant speed. There it is. So acceleration is 0. We look at the forces. The crane force minus the weight equals 0. So the force of the crane equals the weight equals mg. Now keep in mind the differences between the w's. Here I've used a lowercase w for weight, but we're going to be solving for work, which is my uppercase W. Let's first solve for the work when it's lifting straight up. I've called that W sub 1. That is the force of the crane, so C times displacement times cosine of 0 degrees, because it's a 0-degree angle between the displacement and the force of the crane. And that becomes force of the crane. We got up here, mg, so mg delta x. We plug in those values, and we get 146,510 joules. Now we do the work when it's swinging to the right. Well, we have the force of the crane times displacement, which is to the right, but now there's a 90-degree angle between the upward crane force and the displacement to the right. That's cosine of 90 degrees. That's 0. So while it's moving the beam to the right, because it's applying an upward force, but it's swinging to the right, it's actually doing 0 work. So we get the net work equals W1 plus W2, and I've rounded that to 150 kilojoules. Number 14, the world's highest waterfall in Venezuela has a total drop of 980 meters. How much work does gravity do on a cubic meter of water dropping down the waterfall? Well, let's think the work that the gravity is doing. Let's look at the forces on a cubic meter of water. There is the weight pulling down, and there is displacement. And the weight is the force that gravity is pulling on the water. So the work done by gravity is the force of gravity, which is mg, times displacement, times, you notice it's a 0-degree angle between the force of gravity and displacement, so cosine 0 degrees. And so then we have the mass. 1 cubic meter of water is 10 to the third kilograms. That's its density, 10 to the third kilograms per cubic meter. Times g, 9.80 newtons per kilogram, times the displacement of 980 meters, and we get 9.6 times 10 to the 6 joules, or 9.6 megajoules. Now up here on the right, by the way, I've done the calculation for how do we know what the mass of 1 kilogram of water is. We need the density equation. So mass is density times volume. There's the density, but we're multiplying by 1 cubic meter, so 10 to the third kilograms. Number 18, find the work done by a force, 1.8 I hat plus 2.2 J hat newtons, as it acts on an object moving from the origin to the point 56 I hat plus 31 J hat meters. So since it's moving from the origin, from 0, 0, that final location, this actually is the displacement vector. We'll use the scalar product, that work is the scalar product of force times the displacement vector. So here we have the values that were given in the problem. Scalar product means you take the product of the x's plus the product of the y's, and it gives you 169 joules. I'll round that to 170 joules for two significant figures. By the way, you have approximate drawing of where those vectors are pointing. For number 20, we have a graph here of force versus distance. It says find the total work done by the force as the object on which it acts moves, and part A says from x equals 0 to x equals 3 kilometers, and then part B says from x equals 3 kilometers to x equals 4 kilometers. On the picture, I've divided it up, the first leg and then the second leg. Now we have the equation when we have a changing force, that force is the integral of f dx, and we need to know what that function f as a function of x is, and here I've just given it to you, but let's see how I got that. So you can see what I've written in the purple here from basic algebra. You're finding the equation of the line between 2 points, so going from 0, 0 to 340. And for part A, we're just interested in between those 2 points. So we need the slope and the y-intercept. And again, this is something you did in Algebra 1. So the slope is rise over run. The difference of the y's, so 40 minus 0, over the difference of the x is 3 minus 0. We have a slope of 40 over 3. The y-intercept is 0. And so that function is 40 over 3 times x. So that is the force. Now we also have to be mindful of the units. We'll take care of that in the end, but it's not just meters and newtons, it's actually kilometers and newtons. We'll just keep it as 40 over 3 times x. So now we have that the work is the integral from 0 to 3 of the force, which is 40 thirds x dx. You take that integral, and here I've put the 40 over 3. I factored that out outside of the integral. You're taking the integral of x dx, and that's going to be 1/2 x squared, and here I've incorporated the 1/2 into the fraction, making it 20 thirds, and you get 180 over 3, or 60. Now, if this had been meters on the x-axis, it would be 60 joules, because meters times newtons, but this is kilometers times newtons. Or you can think of it as meters times newtons, and then there's that kilo, times 1,000. So we can say that's 60 kilojoules. Another way you could do it without integrating is just take the area of the triangle. It's simple enough to do. This triangle right here, 1/2 base times height. So 1/2 of 3 kilometers times 40 newtons. And you get 60 kilometers newtons or 60 kilojoules. For part B, we're looking at this second part right here. And we could do the area of the triangle. That might be easier than doing the integration. But let's do the integration. We need the equation of the line between points 340 and 40. And the slope, we do rise over run. So 40 minus 0 over 3 minus 4, it's a slope of negative 40. Then we need to find what the y-intercept is. So using techniques learned in basic algebra, we can use this formula, y minus y1 equals m times x minus x1, where we're going to substitute in one of the values of x and y, that'll be for x1, y1, and the slope that we know that it is. So we'll say y minus 0 equals negative 40 times x minus 4. So you can see what I've written in the green, one of the coordinates, so 40. And then we solve for that, we get y equals negative 40x plus 160, and that is the force. Now once we have the force function, we can plug that into the integral. Work is the integral of force, dx, and so negative 40x plus 160 dx, and I factored out negative 40, leaving us with x minus 4.0. And you take that integral through and you get 20 kilojoules. Now, it's easier on this particular problem just to take the area of the triangle as we look in the picture. So it's 1/2 the base, which is 1 kilometer, times the height, which is 40 newtons, and we get 20 kilometers newtons, which is kilojoules. Number 21, how much work does it take to stretch a spring with spring constant 200 newtons per meter? Part A says 10 centimeters from equilibrium, and part B says from 10 centimeters to 20 centimeters from equilibrium. We're going to use this equation that work is the integral of f dx, and in this case with a spring, the force is kx, that's the force that we apply. And so the work to stretch a spring from one length to another length is 1/2 kx2 squared minus 1/2 kx1 squared, and you might want to factor out the 1/2 k, so it's 1/2 k times x2 squared minus x1 squared. In part A, x1 is 0 and x2 is 0.10 meters, and so we plug that in, 1/2 times 200, that's the k, times 0.1 squared minus 0, we get 1 joule. For part B, we're stretching it from 0.1 to 0.2, so it's 1/2 times 200 times 0.2 squared minus 0.1 squared. Make sure that you use proper rules of arithmetic, that you don't just do 0.2 minus 0.1 and then square it. It is 0.2 squared, then minus 0.1 squared, and you get 3 joules. Notice between parts A and B, in both cases, you're stretching it a distance of 10 centimeters. But in part B, it already started farther from equilibrium, and so it actually takes more work in part B to stretch it those 10 centimeters than it did to stretch the 10 centimeters in part A. Number 26, here's a cyclotron. It says a cyclotron accelerates protons from rest to 21 megameters per second. How much work does it do on each proton? We can use the work energy theorem. The work is the change in kinetic energy, which is 1/2 mv1 squared minus the original kinetic energy, but it says it started at rest, so that original kinetic energy is 0. Now we just plug in the values, 1/2 in the front flap of the book. You can get the mass of a proton, 1.67 times 10 to the negative 27 kilograms, times 21 megameters per second squared, and we get 3.7 times 10 to the negative 13 joules. Number 27, at what speed must a 950 kilogram subcompact car be moving to have the same kinetic energy as a 3.2 times 10 to the fourth kilogram truck going 20 kilometers per hour. Okay, so that would be the mass of a fully loaded big rig versus a little Toyota Yaris like you see in the pictures here. And it sets up the problem saying they have the same kinetic energy and we want to solve for the speed of the car. So we'll say kinetic energy of the car equals kinetic energy of the truck, which means 1/2 mcvc squared equals 1/2 mtvt squared, where c is for car and t is for truck. And we're going to simplify that and solve for vc. Well, first we can divide out the 1/2. We're going to get vc by itself in the equation, and you go through the algebra and you should get that the speed of the car is going to be the square root of the ratio of the masses, mass of the truck over mass of the car, times the speed of the truck. Now we plug in all the values. You have the ratio of those masses, square rooted, times 20 kilometers per hour, and you end up with 5.8 times 20 kilometers per hour. So the bit with the radical, what that's showing is that the car needs to be going 5.8 times faster than the truck in order to have the same kinetic energy. So that comes out to 120 kilometers per hour. Number 31. A typical human diet is 2,000 calories per day, where the calorie describing food energy is actually 1 kilocalorie. Express 2,000 kilocalories per day in watts. And by the way, for this typical human daily diet, what you see in the picture is approximately 2,000 calories. That's 2 double doubles from In-N-Out, 4 bananas, 6 Oreos, and a glass of milk. All right, so 2,000 kilocalories per day, we want to turn that to joules per second. And let's do it. We start with the given information, kilocalories per day. Turning into joules per second, meaning we want to turn those kilocalories into joules. Now on the front flap of your book, down at the bottom, it says that 1 calorie is 4.184 joules, and so we'll use that. So we'll turn, first of all, 1 kilocalorie under 10 to the third calories. It makes the kilocalories divide out. Now we'll turn calories to joules by saying 4.184 joules over 1 calorie. That'll make the calories divide out. Finally, we need to deal with the time. So 1 day is 86,400 seconds, and the days will divide out. Now the units we're left with is joules per second, which is watts, and we get 97 watts. What this means is that a typical, as it says, human diet just with daily activity is equivalent of, on average, 97 watts, 97 joules per second. Number 35. How much work can a 3.5 horsepower lawnmower engine do in 1 hour? Well, we're given power is 3.5 horsepower. Let's translate that into MKS units, meaning watts. And 1 horsepower is 746 watts. So we'll do that conversion, and we get 2611 watts. Now the average power is work over time. We want to know how much work, so work is power times time. So we have 2,600 watts. Remember, watts are joules per second, times 3,600 seconds, and that gives us 9.4 times 10 to the 6 joules. Some spring problems here. Number 41. This follows after example 6.4. So I hope you look over example 6.4 in the book. But let's do this problem. Number 41. A cord used in bungee jumping is normally 9.58 meters long and has spring constant 235 newtons per meter. At the lowest point in a jump, the cord length has doubled. How much work has been done on the cord? If it's normally 9.58 meters and then it's doubled, that means that its stretch is 9.58 meters. So x is going to be 9.58 meters. We want to know how much work is done. So there's the formula. Work equals 1/2 kx squared. And you should get 10.8 kilojoules. Number 42 says unstretched, a cord used in bungee jumping is 12.2 meters long. When a jumper reaches the lowest point in her jump, the cord has stretched to 26.3 meters and she's done 15.4 kilojoules of work on the cord. What is the spring constant on the cord? Well, we need to know what the displacement from equilibrium is, so how long it is minus its unstretched length, and so x is 14.1 meters. We'll take the work equation for a spring and solve for k, so k is 2 times the work over x squared. We plug in the values given, and we get 155 newtons per meter. Number 43 is a spring problem, but on a microscopic level. A 2.35 micrometer strand of DNA has an effective spring constant of 1.63 times 10 to the negative 7 newtons per meter. Find the work required to compress the strand so its length shrinks by 1%. All right, so in this formula, the past two problems we've been doing a stretching. Here it's a compression, but because x gets squared, it really doesn't matter to us mathematically whether we are stretching or compressing. X is really going to be negative in a compression, but it's getting squared anyway, so I've just left off the negative sign. X is 1% of 2.35 micrometers, so 2.35 times 10 to the negative 8 meters you should get. And then work equals 1/2 kx squared. You're given the k, we have x, and so you should get 4.50 times 10 to the negative 23 joules. Number 54. A force acts in the x direction, its magnitude given by force equals ax squared, where x is in meters and a equals 5.0 newtons per meter squared. Find the work done by this force as it acts on a particle moving from x equals 0 to x equals 6. All right, well, work with a changing force is just the integral of f dx. We've got the formula for force, that's ax squared, and a later on we'll substitute as 5. And we are integrating with the limits of integration from 0 to 6. And everything here is in MKS units. So let's do the integration. That becomes 1/3 a x cubed from 0 to 6. So 1/3 times, there's my a substitution, 5 times 6 cubed minus 0 cubed, so that's 216, and we get 360 joules. Number 56, a force with magnitude given by F equals a squared of x minus bx squared acts in the x direction. And you can see on the right-hand side of the page how a and b are defined. Find the work this force does on an object moving from, part A says from 0 to 2 meters, part B from 2 meters to 3.75 meters. All right, it's just like the previous problem, just a force that we have to think about how to do this integration. I recommend when doing an integration, if you see a square root sign, turn it into an exponent, just because that's the format that we usually do integration. So here I've put it into the integral, and I've called a squared of x a times x to the 1/2, then minus bx squared. Now we do the integral, and the first part is, remember how to do an integral like this, you raise the exponent on x by 1, and then you're going to take the reciprocal of that new exponent and move it over to the left, factor it out. And so you should get 2/3 times ax to the 3/2 power. I also recommend when doing an integral like this, just to be aware of errors that could be made, I recommend quickly taking the derivative with respect to x and making sure it gives the original amount. And so we say 3/2 times 2/3, those divide out, times ax to the 1/2, and yes, that gives me what I started with. The other one is minus 1/3 bx cubed. And by the way, I'll check my work there and say, take the derivative, 3 times 1/3, those cancel each other out, times bx squared. So yeah, the integral is good. And for part A, we're integrating from 0 to 2, so we get 37.2 joules. Now for part B, we have the same integration. We don't have to do it again. We're just taking different limits of integration from 2 to 3.75. So you'll plug those values in and you get 16.8 joules. Number 59. 2 unknown elementary particles pass through a detection chamber. If they have the same kinetic energy and their mass ratio is 4 to 1, what is the ratio of their speeds? Let's take these two elementary particles. They have the same kinetic energy. They have different masses, and let's call one of them M1, and the heavier one, we'll call it M2, and M2 is 4 times M1. We expect that particle number 1 being lighter will be faster. If they have the same kinetic energy, then it's going to make up for its lower mass by having a higher speed. All right, K1 equals K2, so 1/2 M1 V1 squared equals 1/2 M2 V2 squared. Divide out the 1/2s, and we're setting up a ratio of the speeds because it's asking for what is the ratio of their speeds. So as I go through the algebra, I eventually get V1 over V2 is the square root of M2 over M1. And now I plug in that M2 is 4 times M1. The M1s divide out, and so square root of 4, which is 2. So the ratio of the speeds of V1 over V2 is 2. The particle 1 is going twice as fast as particle 2. And then I go back to what I expected, just to see if it checks out, if it seems reasonable. I had an expectation that particle 1 being lighter will be faster, and yes, here we have that it's twice as fast. Number 66. A force pointing in the x direction is given by F equals ax to the 3/2 power, where a is a constant. The force does 1.86 kilojoules of work on an object as the object moves from 0 to 18.5 meters. Find the constant a. All right, so we've done a few problems like this, but we're solving for something within the force equation rather than work itself. Well, let's do it. Let's set it up. Work equals the integral of ax to the 3/2 dx, and it's a that we're trying to solve for. I didn't write out the limits of integration. I do that in the next line. We take the integral, and that x to the 3/2 becomes x to the 5/2 with a 2/5 coefficient to the left. And here I've put in the limits of integration. So we have work equals 2/5 a. I factored those out to the left. And then we plug in the limits of integration, 18.5 to the 5/2 minus 0 to the 5/2, which is just 0. And then we're going to take everything, we're going to go through the math and solve for A. So we get 1860 joules on the left, because that was given by the problem, equals on the right 588.829 times A. So we solve for A, and we get 3.159. The units are joules per meter to the 5/2 power, sort of awkward units, but let's think about how do we find the units? Well, we do dimensional analysis. And we know that work is proportional to a times x to the 5/2 power, because we see that up here in the second line. So if we want to solve for A, we can say A is proportional to work over x to the 5/2, and then we think, what are the units on that? Well, that'll be joules to the joules over meters to the 5/2 power. Number 67, as we've been dealing with scalar products of vectors. This gives us good exercise in thinking about those concepts. Two vectors have equal magnitude, and their scalar product is half the square of their magnitude. Find the angle between them. Okay, so we have vectors A and B, and if they have equal magnitude, let's just say their magnitude A equals B, I'm just going to call it X. You can call it any letter you want. You could call it A, you could call it B, but I'll just call it X. Now, the problem says their scalar product is half the square of their magnitude. So here I've written that out. Scalar product A times B, A dot B, is 1/2 A squared, which in the next line I'm going to call X squared. The scalar product is AB cosine theta equals 1/2 X squared. And it's that theta that we're interested in. Well, A times B is X squared. It's X times X. And here in this line, you can see the X squared and the X squared, they will divide out. And we're left with cosine theta equals 1/2. So then we can take the arc cosine of 1/2 and we get theta equals 60 degrees. So there's the two vectors. And that is the end of the Chapter 6 homework. Have a great day.